also that we want to continue. And I'll give this time to you to start with your introduction and then present what you have for our members.
Great. Let me just give me just one moment to plug in. Yeah, so 172 years ago, there was a cholera epidemic in London that was curtailed by a physician. And he did it not through a medical intervention, rather he drew a map. And by plotting the deaths on a street grid, he made visible something that the tables of mortality statistics had completely obscured. This outbreak was driven by a single contaminated water pump. So he solved this problem by changing the way the data was seen. And that dynamic is playing out right now across the energy landscape. The energy transition is generating data at a scale that really would have been unimaginable just a decade ago. Flow and material simulations are generating terabytes of data, integrated energy models with multivariate time series of tens of millions of nodes, high fidelity instruments streaming overwhelming amounts of data. We have more data than ever. And this talk explores how advanced visualization technologies are transforming analytical reasoning and knowledge discovery in energy research, drawing on recent work at the National Laboratory of the Rockies Computational Science Center. Through a series of scientific case studies, I'll demonstrate how immersive and high-resolution visualization environments are enabling our scientists and engineers to identify previously unseen patterns and features in their data, insights that often have remained hidden in more traditional desktop-based analyses. So I believe that these environments offer a very unique data analysis above and beyond our more traditional visualization because of how they activate our brain. But let's start with the fundamental question, like, why should we visualize our data in the first place? And it's really more than just communicating our data or communicating our results. It's really about better understanding our data. We should visualize our data because we humans are very good at visual processing. In fact, the majority of our neurons that are in our brain are dedicated to visual processing. And my argument to you today is that we can better visualize our data by leveraging the way those neurons are designed to work or have evolved to work. In 1973, F.J. Anscombe developed Anscombe's quartet to demonstrate the value of visualizing your data compared to only using summary statistics. So the quartet is these four sets of data sets, right? So we have an XY column across four data sets, and they have identical summary statistics to two decimal places, right? So they have the same mean, the same standard deviation, the same correlation, the same linear regression. So that would suggest that these data sets are remarkably similar. However, when we visualize these data sets with a simple two-dimensional scatter plot, we see that these data sets are very different, right? Three of these data sets kind of have linear relationships. Two are heavily skewed by outliers. One has a nonlinear relationship. There are, of course, kind of statistical methods that can tease out these differences, but they require a level of sophistication far exceeding the level of sophistication of simply creating these scatter plots. So we're using visualization because we have this very sophisticated pattern matching machine that sits on our shoulders. We're readily able to identify patterns and anomalies in visual data, and we're able to contextualize those patterns and anomalies with all of our domain knowledge. So let me step through a more complex example with some of our lab data. Here, instead of visualizing 11 points, I'm visualizing 11 million points. This project is investigating kind of thermochemical conversion of biomass. So this is effectively a fluidized bed where we have a bed of sand and we're injecting a steam source in the bottom, and that's creating these bubble-like structures. And inside, we can add carbonaceous material like coal or switchgrass, and that this thermomechanical action actually reduces that into a syngas. But it's the visualization that I really want to focus on here. If we zoom in onto this visualization, we see this fluidized bed is really made up of a whole series of individual spheres. And I think it's easy to overlook two things, right? First, the algorithmic complexity that went into rendering this image, and dismissing the aesthetics of the rendering as merely being eye candy, when in fact I think they're critical to the understanding. Now, the simplest way that we could go about visualizing kind of these 11 million kind of sand particles would be with emissive lighting, where we're just giving each individual sphere a single solid color. And when we do that, we really get no information at all. The next thing that we could do is Lambertian rendering, where here we're thinking about the shape of each one of those sand particles, and then modulating the color of that sand particle based on a normal vector off of each individual point on the sand particles. If we think about what that looks like for an individual sphere sitting on a plane, we have a sense that we've got a round object, but we really don't understand its relationship to that flat plane. And when we look at all 11 million particles, we have no real sense of what we're looking at. To get a better idea, what we really need to do is think about the shadows that are coming from this. So instead of just thinking about a normal vector on each point on the sphere, we think about shooting a ray back toward the sun or to the light sources. And if that ray meets the sun, then we have illumination. If it hits some piece of geometry on the way back, we're in a shadow. So now we have a sense that we actually have a particle sitting on a plane in that upper right. And for the first time, we really have a sense of, some of the structure that's happening inside of this 11 million point rendering. But we can do a little bit better than that and think about the way that, or try to mimic the way that light actually works. So instead of just shooting a single ray back to our light source, we shoot rays in all directions from every point on every sphere. And those rays that reach the sky are going to increase our illumination, and those that hit some geometry are going to provide no additional illumination. And when we do this, we start to get kind of these soft shadows. So on our upper right rendering of a single particle, for the first time, we really have a sense that that particle is sitting directly on the plane. And for our 11 million point rendering, now we're starting to understand a lot more of that structure, a lot more of that concavity inside of those bubbles. But what I'm really trying to get at is like, why does the technique matter? Why is the global illumination on the right so much more successful than the local shading on the left? And my argument to you today is because the global illumination on the right is trying to mimic the way that light works, and our brains understand the way that light works. We're automatically able to parse those light and dark regions and understand that we have these concave bubbles where none of that information is really provided on the local shading. So this lighting and shading that I've just described is a depth cube, and we use several depth cues to navigate the world. Depth cues are what differentiate 3D data from its 2D projection. So here are a whole variety of depth cues: structure from motion. So this is the idea is as I shift my perspective from front to back or right to left, things in the foreground move faster than the things in the background. Lighting and shading, which I just described. Stereopsis, the idea that we have two eyeballs and they both have a slightly different perspective, so we're able to construct a 3D scene. Convergence, the idea that our eyeballs actually we go a little bit cross-eyed when we're looking at something close up, when our eyes go more pale when we're looking at something farther away, and that is giving us a depth cue to how close the thing is relative to us. Ocular accommodation is similar. The shape of our eyeballs actually change depending on how far away we're looking, and that is giving us some feedback. So as an example, the image that you're seeing here, and I hope this comes through on the video share, but the image that you're seeing here is a three-dimensional point cloud, but we're only looking at it from a two-dimensional projection. And what I'm going to invite you to do is try to find the structure inside of this point cloud. And right now, I don't think you're going to see any. But if I start to rotate this point cloud, and hopefully this comes through on the video, what you should be able to pick up is some structure right there in the center of this point cloud. In fact, there's a little rabbit there. And frustratingly, when I stop rotating the point cloud, that structure disappears, even though you know exactly what it is and exactly where it's at. So that's that structure from motion, right? And that's ultimately what we're trying to do with an immersive environment. This is an environment created with a combination of hardware and software that provides the user with a psychophysical experience of being immersed in a computer-generated scene. And then immersiveness is kind of based on a variety of factors. The fact that it's egocentric, that is, that as you move, you're able to move through the scene. Kinesthesia support the idea that we have awareness of our own bodies relative to the data in the scene, a very wide field of view, the resolution, the fact that it's stereopic, and the fact that we can manipulate things directly in 3 dimensions. So now I want to lead in with some examples of how we're using kind of this immersive space, right? A vast majority of the work that we're doing is in materials design. And in fact, this is where we've really seen kind of improved spatial judgments based on using kind of these capabilities. The very first thing that we ever put into this space was an OPV morphology. So what we're looking at here is the bulk heterojunction. So this is the active layer of a solar cell. And this is 2 materials, a polymer and a fullerene, and they've been annealed together, represented by the 2 colors, and they get all kind of mixed up. And then for the visualization, what we've done is we've taken the backbone of those 2 materials. All right, so we're just kind of looking at a skeletonization. And the idea is a photon comes into this material, there's an excitation, and that photon separates into an electron and a hole. And then those 2 charges are going to flow down these 2 different colors. And if they reach their electrodes, then they have charge. If they meet back up in the middle, then you have a less efficient solar cell. So what we were doing is we were simulating hundreds of thousands of these materials on our high-performance computer, trying to select just 1 or 2 that we might want to go synthesize in the laboratory, right? We were looking at a whole variety of statistics to try to determine which one of these might be the best candidate to go spend the expensive work to go actually build one of these materials. And it was the very first thing that we ever put into our immersive space. And the PI was very excited when I said, hey, I got your data in the space. I really want you to come and take a look. And he was like, oh, this is going to be a great way for me to show my program managers the type of research that I'm doing. And he came in and he put on the glasses and he said the 3 most exciting words in science. Huh, that's funny. What he appreciated for the very first time was the heterogeneity of these junction pathways. So if you look over my left shoulder there, we've got kind of 6 different pathways coming together in blue. But then if you follow the one that goes in front of me, the next junction pathway only has 2. So this was the big aha moment for the PI. He noticed that these junction pathways would really speak to the degrees of freedom that those charges had to flow through this material. So it completely changed the way he was doing his statistics on these data. Right now, he wanted to understand the distribution of these junction pathways across all 100,000 different materials. So we're right back to what Anscombe said, right? That we wanted a qualitative understanding of our data in order to go and develop those quantitative methods, right? For him having a better understanding of what his data were, now he's able to go and actually develop kind of the statistics he needed to tease them apart. Here's another example from OPV material science. Here we have 2 polymers, kind of the red bits in the last visualization, and these had been synthesized in the laboratory. And through some XRD imaging, they believed that both of these polymers exhibited something called pi stacking, the way the polymer kind of folds up on itself. Then they did some very high quality visualization of these 2 polymers, trying to identify if in fact they were both pi stacked. But it wasn't until they stepped into the environment and stuck their head directly into the polymer that they were able to basically definitively and immediately identify that this one was pi stacked and the other one was not. So there's something very interesting going on here, right? If we step back, they had a very sophisticated visualization, right? They have both a very nice lighting model as well as a structure from motion, right? So why was it that this structure from motion, we weren't able to identify the pi stacking, but in this structure from motion, we were? What we think is going on is something called embodied cognition. And that's the theory that suggests that thinking is actually an inseparable combination of our bodies and our minds, that higher level cognitive functions have been empirically tuned both phylogenetically and autogenetically, that is, through the evolution of our species, as well as learned over our lifetimes by our physical perception and our physical interactions with the world. So to say that in a different way, our capacity to reason has emerged from various sensory motor experiences. And there's a whole variety of evidence that supports this. For example, several neurophysiological studies show that high-level reasoning activates areas of our brain that are predominantly concerned with motor control. And there are behavioral studies that suggest that sensory motor knowledge actually affects both language and numerical processing. So really what we think is when we're inside these immersive environments, when designed right, we're activating parts of that cognitive machinery in ways that a desktop computer does not. And where we've seen this is in computational fluid dynamics, where we're able to kind of directly seed particles inside the flow and watch where that flow goes. And kind of through that, we've been able to identify aspects of that flow that we never saw on a desktop. We've been able to see this by kind of embedding very high dimensional spaces inside the immersive space, allowing our engineers to actively explore kind of these high dimensional representations. A lot of work in grid monitorization, thinking about ways that we support, again, kind of these really highly multivariate spaces, using this extra degree of freedom that's afforded by our immersive space. And more and more kind of in the sense of immersive digital twins, where we have some real-time simulation running in the background, and we're able to manipulate that simulation in real time to either understand kind of the state of a system or kind of what-if planning. If we were to manipulate a system in a certain way, what would the impacts of that be? Now, all this has been kind of centered around kind of that large-scale immersive space. But more and more of these headsets are coming onto the scene. So in these images, we're looking at the second version of the Magic Leap. We're also using the Apple Vision Pro. And these offer some advantages over the large-scale environment in that they're mobile, and we kind of take them kind of into the laboratory spaces. And what that's allowing us to do is do situated visualization, where we're able to effectively draw the visualization directly on the equipment that we care about. So for example, in the image in the bottom right here, we're looking at a visualization of a PV module. So we can see the power flow through the PV module, and as I manipulate that PV module, either by changing its orientation to the sun, I can see how that changes its output, or I can shade that module and see how that changes, kicks on the bypass diodes, shades certain cells, etc. So at this point, you might be, really excited about immersion, but I would caution that immersion isn't always better, right? So here was a very kind of tangible example for us, right? So what we're looking at is some hydrogen adoption across the United States, where each cylinder is sized by the amount of investment that's been made at various locations across the country. So I want you to kind of think about this visualization for a moment and think about, if I'm trying to ask or answer questions about kind of the relative investments across the United States, this is a really poor visualization because I have to really move my body to understand kind of all of the data. While if I look at this visualization, I can see all of this data simultaneously. And in this example, if the question I'm trying to understand is the geographical distribution of investment, this is a fairly good visualization. But if I don't care about the geographical distribution, I'm just trying to understand the distribution, this is a better visualization. So it's really key that we think about what we're trying to understand from the data when we're designing those visualizations. So from an immersive standpoint, where we're really seeing the benefit is those improved spatial judgments, right? That we're able to kind of see these qualitative structures in ways that we can't see on a desktop computer. So the improved spatial judgments. We're also able to kind of see, or we're able to directly manipulate those data directly in three-dimensional space, right? So we're moving, if we have a three-dimensional object and we want to manipulate it, it's much more natural to manipulate it in three-dimensional space than rather using a two-dimensional mouse. And then finally, the ability to embed higher dimensional data into these spaces. Now that's half of the kind of advanced visualization that we're doing in the lab. The other half is really high resolution data, right? So we have this high resolution display wall, 100 million pixels. So that'd be like 16,000 pixels across and 6,500 pixels high. And here what we're trying to do is provide both the visual resolution as well as the visual fidelity, or kind of the real estate and fidelity, to see the forest and the trees at the same time, or the context and the details. Where there's a whole variety of research out there that shows that these kind of large field of views improve our spatial acuity and our spatial memory. We're able to kind of offset some of our memory onto the wall when we're doing analytical reasoning. To give you a sense of the scale of this display is the orange bit, where we have 12 4K displays as one unified image. The 4K display there kind of in the bottom right, and then an HD display, which would be more typically what you have on your desktop. But one of the keys here is this image, this display is about making little pictures big. It's not about making big pictures visible. So if I take a regular sized image, like the shot of this baboon, and I scale it up, all I get is this horrible pixelated image, right? What we're really trying to do is take very large data and find ways to look at those very large data. So for example, this is a metrology study where we have 416 time series at 2 Hertz for 48 hours. And if I plot those data and you're within about 12 feet of the screen, you're able to make out all the individual traces of all those 36 million individual points of data while seeing the trends across all 416 time series. But if I take those same data and I shrink them down to 4K, which is kind of what I've done there in the middle, I lose the individual details. I can't see the details anymore, but I can still see the trends. And if I shrink that down to HD, then I've kind of lost both, right? Give you a better sense of what that might look like. So on that 100 megapixel display, right, I can see each individual trace. 4K, I lose the individual traces, but I still see the trends. HD, I kind of lose them both. So that's what it's really about, is we're trying to see kind of the forest and the trees at the same time. Where we predominantly use this display is in city scale distribution modeling, right? Where we're trying to understand power flow across very large geographical areas. So one of the areas that we concentrate a lot on is like the San Francisco Bay Area, where we have a very large distribution model with 14 million nodes. And we're trying to understand how power is flowing between those nodes. So why does the scale matter? It's because the questions that we're trying to answer require that resolution. Where should the EV charging go? How does rooftop solar across this region impact controls and controls equipment, for example? The key architectural insight is we're using kind of different data strategies for different tasks here. For static reference layers, kind of the bones of the network, we use vector tiles that let you zoom in from kind of a continental view, the whole of the United States, down to a neighborhood seamlessly. So for live simulation outputs like voltage, we're updating every bus, and we encode these assets into a binary GPU buffer. And that's how we hit kind of sub-second rendering times on these 14 million assets while keeping the map interactive. The result is analysts can explore kind of distribution adoption scenarios, watch voltage violations propagate in near real time, and switch between kind of feeder level and substation level views without the data ever really becoming the bottleneck. The core tool here is using Tippecanoe, so it's a C++ type pipeline that takes the raw data and then generates a tiled directory, and then that tiled directory provides us a hierarchical way of manipulating those data layers. So the question isn't always, can we show the data? Often it's, is the way that we're showing the data going to lead the analyst to the correct conclusions? So we've already talked about that in the 3D perception. But even in 2D, visual encodings are not neutral, right? The choices we make, the color, the shape, the interpolation method, the spatial layout, they don't just change the aesthetics, they're changing what kind of our analysts see, what they miss, and ultimately what they're going to believe. So I want to do a little bit of a deeper dive kind of on the image that's on the left. So many of the visualization techniques that are powering the power systems engineers rely on today were largely developed for a different kind of grid, right? A simpler one where electricity flowed in one direction. Generators were large, they were utility owned, and the models had hundreds of buses, maybe a few thousand. Now we're modeling systems with tens of millions of buses, rooftop solar on individual homes, EV charging loads in the neighborhood, and distributed resources that aren't owned or controlled by our utilities. So the data has grown by orders of magnitude, but the visualization techniques have not kept pace. And we're using tools that were designed for kind of a sparse, simple grid to analyze a dense, radially complex one. And that mismatch has consequences. So here's the core of the problem. And I think it's something that's not obvious until you look at it closely at a distribution network topology. So these blue lines are what are connecting kind of all the individual assets in a neighborhood. And here we're looking at kind of the San Francisco Bay Area. And in a power system, what really matters is electrical distance, how two buses are connected through the network. But most of our visualization techniques use geographical distance. That is, they're drawing the smooth gradient between nodes that are physically close to one another on a map without any consideration to how close they are electrically. In a transmission network, that's often a reasonable assumption, right? Nearby buses tend to be electrically nearby too, but in a distribution network like the one that we're looking at here in the San Francisco Bay Area, the kind that are dominating kind of these urban systems, that assumption completely breaks down. In this example, I've highlighted two pairs of buses that are only about 100 meters apart, right? But geographically, if we follow their closest paths to one another on the electrical lines, they're over 4 kilometers apart. So the problem now is if I try to show this, show the voltages that are on this system using a geographical color map or geographical heat map based on the geography, it's going to be completely skewed. To understand how widespread this issue is, we did a systematic review of how contour mapping has been used in power systems literature going back to 1999. And across 45 papers, these contour maps appear for kind of three main purposes: getting a system overview, identifying outlying values, and tracking event propagation. Voltage and frequency, by far the most common values being visualized. And two things jumped out. First, the scale of the systems being visualized has grown by 3 orders of magnitude, from under 100 buses to tens of thousands. And then second, the rainbow color map. The rainbow color map lacks a perceptual order and introduces kind of misleading gradients. And it remains stubbornly common despite decades of visualization research recommending against it. So the field has been applying this technique developed for small sparse systems to large, dense, topologically complex ones. And when we surveyed the power system engineers, they believed that these heat maps were effective for the systems that they were looking at. So we decided to test this more rigorously. We took a 24,000 bus distribution model from the San Francisco Bay Area. So just focusing in on these 6 or 7 distribution feeders. And what we did is we introduced kind of 15 known voltage violations, and we looked at 2 ways to represent the system. On the left, we represented it just with a simple glyph, where every bus is represented directly by a circle that's scaled and colored by its value. And on the right, we have this standard voltage, heat map or contour map. When we quantitatively compare the 2 techniques, we see that the standard contour map is dropping the tails of the distribution. It's effectively averaging out those extreme values. And critically, these power system analyses, it's the extreme values that we actually care about, right? And the mechanism here is straightforward, right? The contouring algorithm is using an inverse distance weighting. So each point on the map is an average of its geographical neighbors. So mathematically, that means the most extreme values in your data are always going to be reduced. The tails are always going to get clipped, violations hidden. And that's not a bug. That's because the algorithm works by design. In a sparse transmission network, this averaging might be acceptable, but in a dense kind of distribution system here, it systematically erases the exact values that we're looking for. But not in a uniform way, right? So I'm highlighting two different regions here of the map. In the south, we can see kind of the minimum actual value compared to the minimum graphical value is very close, right? But in the north region, it significantly curtailed that tail. And that's all a function of that topological complexity, right? So the fact that we have more topological complexity there in the north means we're more heavily skewing those data. So it's harder to understand, what's actually being represented. So again, we asked professional power system engineers to find the voltage violations in these two images with control groups. And the results were stark. With the contour map, engineers only found an average of 5 of the 15 violations. And with the glyphs, they found 12, right? So it's not a marginal difference. That's a difference between catching a third of your problems to catching most of them. And the effect size was enormous, right? It held regardless of which visualization the engineers saw first. So what makes this worse is the engineers felt more confident using the contour maps. So you have a visualization that's simultaneously less accurate and more convincing. And that's a really dangerous combination in kind of any operational context. So let me try to draw a thread through everything that we kind of talked about today, right? Because we've moved across a lot of ground, from material science to grid monetization, from immersive 3D environments to a 100 megapixel display wall. So on the surface, those might seem like very separate stories, but I think I'm trying to make the same argument. The first part of that argument is about capability. Traditional desktop analyses have a resolution limit, not just in pixels, but what the human perceptual system can engage with, right? When you put a scientist inside of a data set, inside of an immersive environment, or spread 12 million grid assets across a wall-size display, you're not only showing them more, you're changing the cognitive act of analysis itself. Patterns that are genuinely invisible on a desktop scale, structural features and materials, or cascading behaviors in complex systems, spatial relationships across a distribution network, they become apparent, right? The environment is doing the analytical work that the algorithms were not finding. The second part of the argument is about trust. Capability without rigor is dangerous, right? We showed that the most widely used visualization technique in power systems, the one that engineers use daily and feel confident about, was in fact causing them to miss 2/3 of the problems that were in front of them. Not because the data was wrong, but because the encoding was, right? The visual design was an epistemological choice. The color map choice, you pick, the interpolation method you use, the spatial layout you assume, each one of those is a claim about the reality, and each can be wrong in ways that you can mislead even kind of trained experts. So the full picture is that advanced visualization gives us the ability to see things that were previously hidden. But that ability is only as good as the perceptual and cognitive validity of the encodings we're using to reveal them. Immersion and resolution buys you access, but rigorous design really determines what you see. So I thank you for your attention. Happy to answer any questions.
Thank you, Dr. Kenny. It was a very deep talk, covered a lot of ground, as you said. Yeah, if anybody has any questions, please feel free. You can ask your questions. So I'm a software engineer, Dr. Kenny, and I work pretty much not in these huge data sets, but very few data sets. But when you're building these big immersive analytics interfaces, you build in massive amounts of um, streams of data, right? And um, in order to do all these things, how do you architect all the backend pipelines and everything for the data to come on? What programs do you use? What software do you guys use it?
Yes, I can start with the software. And it's very depending on which environment we're in. But in the immersive environment, one of the ways in, in a lot of the headset environments, so the head-mounted displays like Unity, which is a game engine, is kind of the leading player right now. That's where most people are doing their development. And in the early days of our cave, we did try kind of a Unity backend, but we found that it really wasn't performant for the scale of the data sets that we've been using. So we abandoned Unity and just built our own. For years, we used kind of OpenGL and C++, kind of a homegrown backend. And then just in the last year, we're migrating away from all of the OpenGL and C++ backend, and we've developed a new backend using Rust and Bevy. But again, all that's homegrown just to really kind of keep things kind of fast and performant, that we're able to look at these very large data sets that we really can't look at in more of the kind of the game engine kind of space. Um, a lot of the way that we support these really large data sets is effectively by cheating. We just throw more money at hardware. Right. So we do run like our immersive space as well as our kind of large scale display wall with very large servers. So these are very large servers, where each screen basically has a dedicated kind of RTX graphics card. The server itself, has a couple terabytes of RAM. So we rarely bump our head when we're kind of doing a lot of the visualization techniques. We can do that a lot of that visualization kind of right there, kind of on chip. And then that visualization server is connected just across the hallway to our high performance computer through 100 gigabit fiber. So we directly mount our high performance cluster and our parallel file systems with 100 gigabit fiber. So we eliminate some of the hard work, by using kind of big iron effectively. On the 2D side, a lot more of that is web, which surprised us. Like, we've been doing a lot more work in WebGL and WebGPU, and are able to support kind of that 100 megapixel display predominantly in web.
Okay, got it. Yeah. And I see that you have a special glasses that is for the 3D spatial visualization. I mean, even on your profile picture on the vTools, we see that you have a special glass that has antennas kind of a thing around.
Yeah, I don't know if I have a good good picture here. Let me see if I can.
Yeah.
Yeah. Yeah, I mean, so effectively, I don't know that we'll be able to see it in this video, but there are cameras that surround the screen. You see one of these little circles here in the bottom right, and what that is an IR strobe with a little camera in the middle of the strobe, and there's 6 of those. And what those 6 cameras are doing is they're kind of flashing. The strobes are kind of flashing the scene, and looking for little markers that are on those glasses. So we have 6 little markers that are on those glasses. And kind of based on their orientation, we're able to triangulate the position and orientation of those glasses in the scene. So then as I move through the scene, I know kind of where I am in the scene, and I change the camera location for the 3D visualization. And that's what's giving us that sensation of presence with the data as we move through it. That's what's giving us that motion parallax, right? So as I move through the data, I have a sense of where I'm at, because of the position of those glasses. Now, what's not actually happening in this visualization, but what is typically happening is we do stereo. right? So we're actually putting up two images, one for your right eye and one for your left eye, and we're doing that at 120 hertz. And then the other thing those glasses do is they're shutter glasses, and they're synced with that 120 hertz. So what happens is they block out the right eye when I'm showing you your left eye image, and then they block out your left eye when you're showing the right eye image. And they do that kind of in sync, right? So now all of a sudden it tricks your brain because your brain's getting a right eye image and left eye image. So now you get that stereoscopic viewpoint as well as that motion parallax. So I'm adding those two bits of those two different depth cues to the scene, both the stereopsis as well as the motion. Now, what's surprising to a lot of people is that structure from motion is a much stronger depth cue than the stereopsis, right? So in fact, what I can do is and have done, only anecdotally though, is like we can put somebody in the cave where they have stereo and kind of that 3D tracking, and then you can turn the stereo off, and most people don't notice, right? They don't notice they've lost kind of that 3D vision because they still have that motion parallax. But it doesn't work in reverse, right? If I turn off the motion parallax, stop tracking, then all of a sudden they really lose that sensation of presence, even though they got a 3D projection from their two eyes.
I see a question in the chat. They're asking, are there special cameras used, and what is the pixel on those?
Yeah, so the cameras that we're using are from Viacom, so it's a commercial. They're commercial cameras, and they're actually sold for motion capture. So these are the same little markers that you'll see for Hollywood movies. You'll often see kind of the actors kind of in these black leotards with little reflective dots kind of all over their face or all over their kind of leotard. We're using that same system, but here, instead of trying to track the rigid body, we're just kind of tracking in the glasses. And if I kind of go back one of these, yeah, in this example, you can see I've also got those little markers on my joystick. So as so I can manipulate things directly in 3 dimensions using that joystick. In fact, we're able to develop a whole variety of different user interfaces. So there was an example where we were allowing people to build a concentrating solar collector so they could move struts and a rivet gun in. And we had basically made lots of objects kind of out of foam rubber and then put these little markers on those foam rubber objects so they could, pick objects up, kind of move them into the scene, kind of rivet them in place, kind of things of that nature. So it's pretty wide open to what we can manipulate kind of in that 3-dimensional space, as long as we're able to put markers on them and put those markers on them in a different orientation than anything else that's marked in the scene, right? The cameras themselves, I think, are only a few megapixels. But again, like I said, it's kind of a standard kind of commercial product that's sold predominantly to the motion picture industry. We're just kind of subverting it for our own use. The image that you're seeing there is actually 6 projectors, right? So we have 4 projectors behind the glass, and we have 2 projectors that hang up in the ceiling that project down, and each one of those projectors is a 4K projector. But there is a little bit of a blend zone that is, those projectors overlap to give you a seamless image. So we lose about 10% of the resolution kind of in that overlap. So it's not quite, 6 times 4K.
Yeah, thank you.
With your study being in such a aggressive area, the Bay Area there, I'm curious, is there any increased infrastructure development needed in more rural areas if you were trying to take this concept to the national scale, like in rural Midwest region? Do you have this data readily available, or would you need to implement technology to acquire it?
Yeah, so so down to kind of the parcel level, which is kind of the distribution level, we have a couple different types of data sets that we use. So oftentimes we're directly partnered with the utilities So LEWP is a good example of that, where we directly partner with LA, and we have their, whatever it is, 4 million asset model, and we're able to kind of run simulations against kind of their direct infrastructure. But in that instance, we're only really allowed to use those data when we're asking and answering questions about LA. So if we want to ask more general questions, we use a model like we have here in the San Francisco Bay Area, where this is a synthetic model where we've effectively built up this big distribution system based on kind of all the public data that's out there, right? So we know, we have information on every parcel. We know everything about the road networks. We have pretty good information about how PG&E builds their distribution systems. So based on that, we can build this big synthetic grid. And in fact, the lab is trying to build these synthetic grids across the United States, so we can kind of ask rural questions versus kind of big urban questions. And those questions are very different, right? So if you have a lot of density like you have in San Francisco Bay Area, that tends to have kind of different challenges than if I go back to this visualization. The bottom visualization here is of a rural feeder in rural North Carolina. So kind of the impacts on the distribution system kind of in that rural area definitely are different than kind of some of the concerns that we have in the urban areas. And a lot of that is because the distances of those electrical lines tend to be a lot longer, so we tend to have more voltage challenges on those systems.
Thanks.
Yeah, I see our section chair, Alkesh, also on the call. Alkesh, do you want to talk a bit? Yeah. Okay. Yeah, Dr. Kenny, I think I don't see any questions. And I just came to know that you also have a project here at New York's Power Authority here, Agile Lab in Albany. And you do frequently travel to Albany?
Yeah, that's right. So New York Power Authority, they have their Agile Lab, which is in Albany, and just earlier this summer, they've installed a big cave-like system. We designed it very similar to the one that we have at the lab. So it's kind of this two-surface display, a floor and a back wall. And there we're developing kind of these immersive visualizations, similar to what we've seen, except there we're really concerned with kind of the dynamics of the power system. So they're developing a digital twin of the New York bulk system, their transmission system, and then we're tying that digital twin directly into that immersive cave. So we haven't made any of the videos or images public yet, but hopefully that'll be soon. But I am in the kind of that area of New York every couple of months to kind of touch base with the Agile Lab and the work going on there.
Yeah, actually, we would like to have you in person for a talk. If you're here in Albany, that would also be amazing. So we can schedule something. And
Yeah,
also,
yeah.
I just want to ask you about, is there any development using AI, in the space of visualization and all that research?
Yeah, certainly, AI is kind of getting its fingers kind of into every little bit. We've been using AI for quite some time. In fact, the visualization that we're seeing here in this image was based on an AI surrogate. The idea being that some visualizations, particularly if we're talking about a digital twin, a lot of the models are too slow to run in real time, right? They're very large models on HPC that they may run on that HPC for many hours or days. But for a lot of these digital pins, people want to go and kind of ask interactive what if questions like, okay, I can see the current state of the system, and now I want to go add a battery or change something about a circuit. And the problem with the kind of the big HPC models, it may take many hours kind of to run that model. So what we've done for quite a while is taken a large corpus HPC models and then train an AI surrogate on them. So effectively, you have this very small, lightweight surrogate that's a representation, right, of those larger models that's just kind of been trained across all of a whole series of scenarios on that, high fidelity model. And then what that allows us to do then is go into the immersive space, interactively manipulate that surrogate, effectively explore the parameter space in real time. And then once we have a sense of like the interesting questions or issues, we can then go and take all that and put it back into the high fidelity model in the HPC and rerun it in high fidelity just to give us more confidence in the answers, right? To make sure that we really haven't got outside of that training data, that we really have gotten the correct answers, but we'll get a much more precise answer when we put it through the high fidelity model. So that's an example of how we're using AI kind of in the visualization space, is really allowing people to kind of manipulate these models in real time.
Thank you, Dr. Kenny. I think if anybody has any questions, this is the last chance, or else we can drop off. So, but Doctor, thank you so much for this talk, Doctor. And yeah, I think having all this visualization and everything, we'll have great analytical reasoning and a lot of knowledge discovery, because a lot of people are visually learning persons, so we easily understand with all these things. And thank you for this talk. Thank you for this time, and we hope to have you again in future.
Great, my pleasure.
Thank you. Thank you.
Thank you.